Hello, how are you doing?
Hi, Professor.
Yeah, it says Zoom user. I wasn't sure who it was.
Yeah, I don't know why it says that. Kind
It's
of
okay.
weird.
Yeah. How are you doing? You have a good weekend?
Yeah, I did. It was pretty chill. I had yesterday. I had a bunch of exams though. It's kind of
Oh, yeah.
stressful.
That's
Yeah.
week 8 now. Yep.
I had pre-calculus exam and biology exam.
Mm. Well, once it's over, then you can relax. So
Yeah.
that's good. Hi, Adrian. How are you? But yeah, I'm just getting over a cold. I'm actually at home instead of usually I'm on campus by now. Um, I have a class earlier that I had to Zoom with them, but they had to cancel it officially in the book because, it's a regular on-site lab class. Yeah, so it's just the weather changes. So one of my students in the night class, he was sick. Um, and I've been working like really long hours and things, so that probably took a toll.
How many classes are you teaching right now?
We're required to do depending on the units, but if a faculty teaches 3 units, we are required to do 5.
Uh,
So some of them are doing 4 with the higher unit courses, depending on the lab and the lecture hours. So I am teaching 5, mostly all 3 units, and then I have a work experience course that I use for apprenticeship program in the IT cybersecurity. Those students, they are in that class to get ready to get hired as apprentice. They go through the apprenticeship program, which gives them free tuition and also be able to take the certificate programs and get job in the field. um, so we also partner up with Cal State San Bernardino for students to also transfer and do pre-apprenticeship for the student before they go to Cal State San Bernardino. So
is that a class or a program? Seems like
it is a program, and then it's a work experience class that is designed to help student get or student work while they're in that class.
okay.
So yeah, so I have a few that are getting ready for interviews, and then I have a few that are working on their. So before they get interviewed, they have to pass the practice test for CompTIA A plus,
Mhm.
and with an 80%. Basically, it's hardware and computer maintenance. So as far as right now, about 50% of my class are getting ready to be hired, and then 50% they're on queue for interviews. So it depends on the employer. Sometimes they're fast, sometimes they're slow. The ones that are interviewing my students is Loma Linda University Hospital. They are going to bring in a couple candidates for apprentices to do their cybersecurity specialist. So they will learn the basics all the way to more advanced level while they're there. And the apprenticeship is they can work from 6 months to however long that it takes them to finish a certificate program. Um, so like 2 years, 144 hours maximum from what I remember or more. Yeah, and it's paid. So
Sounds pretty good.
yeah, I tried to, I'm gonna try to bill out the computer programming one, the
Mhm.
certificate for Moreno Valley. Um, I'll talk to the apprenticeship director. We've been talking about it before to really build the apprenticeship for computer programming. But there's not an existing program in state or the system in the Department of Labor for it. So we have to if we submit it, we have to validate and make sure. And then with that, we have to find the employers to be able to hire programming students. So that will be another area. I'm doing some stuff with crime analysis with digital forensic. um, we're going to do an apprenticeship for that, for the digital forensic side. And then I will work on the computer programming one. We'll see how it's gonna go. It usually takes a little while. Whenever it comes to state and offices, it does take a little time. Okay, it's 6:03. Welcome back. We are in week 8. Exciting, right? Some of you are going through midterm right now, and I know it's intense and crazy. So let's do some screen share, and we're going to talk about our class. So, okay, so in this week, we are going to cover sequence and series. And sorry for those of you who submitted the extra credit, I got to go back and add your points. I haven't done that yet. I remember, but I got to go back and double check. Okay. So in this week, we are going to do sequence and series. And there are a few videos from YouTube that I pull for progressions and sequence and sum. You can check those out when you have some time. We are going to cover chapter 11 this week. I will post the videos. So right now, what we're going to do is we're going to take care of the notes, and then we're going to go over the assignment questions. And then on Thursday, we are going to do a lab with sequence and series in C++, so you can see the approach. So you would know how to be able to write a program for sequence or series. Okay. All right. So for our notes, we would start with defining what a sequence would be. And a sequence is an enumerated collection of objects with the repetitions in that, compared to what we've seen with sets, this container does allow repetition of element values. So you can use a vector, you can use an array, you can use any form of container that would be able to store a collection of objects. And you would be able to use some kind of loop to access the elements in that container. Now, the number of your elements would be considered the length of the sequence or the length of the container. So when you're looking at an array, right, the length of the array is going to be the number of elements that you are going to use. And also, you can have the same elements appearing multiple times across. So you can have like a 100 at the beginning and a 100 at the end, and so on. But in the case where if you're looking at a sequence, and we're going to talk about progression, there is a form of function where we would look at as the domain of the consecutive sets of integers. So when we're looking at a sequence, it is a group of values that would have something in common, right? In a form of progression, how it changes from one value to the next. And so therefore, that would be considered a domain of consecutive set of integers. So when you're looking at the functions, and we can treat this like how we talked about our search and sort last week, where we would look at T of n. And so you can say that you can have a sequence with the progression of 1 with all your integers going from 1 through 100, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. So the A of n is going to represent the actual element, where n is going to be the position of the element, right? So when we look at the array, A of 0, right, would be treated as first. Compared to mathematics side, we would say A of 1 is going to be the first element. So when you look at example 11.1, you have 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, and 1 over 6. And you ask yourself, what is the pattern, right? What is happening with the value when it goes from one element to the next? And we can say that the numerator, which is the top number, stays the same. The denominator, the bottom number of the ratio, increases by 1, right? So we can say if n is going to be 1, if it's the first element, then the first term is 1/1, n is 2, the second term is 1/2, n is 3, the third term is 1/3. So what would be the seventh term, right? We would know that it is 1/7, at it is 1/n, right? So for those of you who like pattern, sequence is great, right? You can automatically see it right away, and you would be able to come up with a function that would represent that sequence. So ultimately, we want to either write a function that represents our sequence or a recursive function that represents our sequence. Okay. So in this exercise, this example, we look at the values in our sequence. Then we would determine what would be the formula or the equation that would represent that sequence, which is T of n. So we can say that T of n is going to be equal to 1/n. So for the 100th term, we would say that it will be 1/100. That's really easy, right? It's easy when it's very transparent. It's easy when you see. And in this case, we do have a progression from one number to the next. Okay, and we will get to that. Let's look at example 2. We have 2, 4, 6, 8, 10, 12, and so on. So there is a progression, right, from one number to the next. So we would start with saying if n is equal to 1, we would take 2 multiplied by n, or 2 times 1 is going to give us 2. If n is equal to 2, we would take 2 times 2 is going to give us 4. N is 3, 2 times 3 is 6. And then if n is 22, we would take 2 times 22 is going to be equal to 44. So the term after the 6, which is the 7th term, then we would take 2 times 7, which gives us 14, right? So after 12, you would see that it would be 14. So then our T of n is going to be 2 times n. And in this case, we would take the n value and multiply it by 2. And we would define arithmetic geometric progression shortly. Any question with example 11.1 and 11.2? Okay, no question? All right, let's look at another example. So now we would have a sequence that would be 2, 4, 8, 16, 32, 64, 128, and so on. And you see this when we worked on the binary conversion, right? So you automatically would know already. So when you approach this type of a problem, you would start with the base case, and then you would build it up. So we would start with the n is 1 for the first value, the first element, right? What is it? So if n is 1, we would have 2 to the first, it's going to be equal to 2. So the n value becomes your exponent in this example. If n is 2, then we would raise 2 to the second, gives us 4. If n is 3, we would raise 2 to the third, that would give us 8, and so on. So the term after the 6, which is the 7th term, we would have 2 to the n, or 2 to the 7. That would give us 128. And so you can find any value in that sequence. Let's say 2 to the 100th position would have 2 to the 100, right? That would be at the 100th position in that sequence. Okay, so in this case, what you would see is we would have n as an exponent to our base, which is the 2. Okay. Now, sometimes you are going to have a sequence that doesn't start until the later element. And you do see some cases where you would have like a 1 and a 1, and then after that, you would have some progression. Okay, so not all sequences are going to start from the beginning, the first element, and it's going to naturally progress. No, right? We do have some sequence that would be a little different. It's unique in that it doesn't start until the later element. So in example 11.4, we would see that we have 7, 8, 9, 10, 11, 12. This is easy because you can see that it starts at 7 and then we naturally progress by adding 1, right? But we have to translate that to how your n is interpreted, because if we say n plus 1, that's not true, because if we take n plus 1, that would not be 7 for the first value. Okay, so our case would be if n is 1, we would take 1 plus 6. That's going to give us 7. If n is 2, that will be 2 plus 6. That gives us 8. And if it's 3, 3 plus 6 gives us 9. So we have to build our function around the element position or the, the n, right? So now here we can say that in the 7th term, at the 7th location of the container, right, we would take n plus 6 or 7 plus 6, which gives us 13. Okay. So in this case, we would take the n and we add it to a value. And I want to expose you to quite a few examples before we start our assignment. Okay, so it gets a little easier if you start seeing some example and the pattern in different example. So for, yeah.
Sure, I'm sorry, I have a quick question. For that last one, just for clarity, if we're saying 7 plus 6 and we're at 13, does that mean at the 7th element, it's 13 is the value
Yes.
that's there? Okay, all right,
Yes.
got it. Thank you.
So we can say at the 27th element, right, it would be 27 plus 6. Good. Then 11.5, right? We have 1/2. So we have half to start, and then we have 1, we have 2, we have 4, we have 8, and we have 16. And that's the beginning of the sequence. And it can go infinite, right? We know that some sequences are finite and some sequences are infinite. So because you do have all types of different numbers that you work with. So in the case where you're looking at data sets, right? Let's say user data sets, you would be able to have more data continuously added on every moment, every second, every day as the user use the application or the device and so on. So in example 11.5, we would say the first value when n is 1, we would take 2 and raise it to 1 minus 2, which gives us 2 to the negative 1 power, which gives us half. If n is 2, we would then again take 2 and raise it to the power of 2 minus 2, which is equal to 2 to the 0 power, or 1. If n is 3, then we would take 2 and raise it to the power of 3 minus 2. That gives us 2 to the first. That gives us 2. So now we can say that when we get to the 7th location of that container, the 7th element, right? We would take 2 and raise it to the 7 minus 2 power, which gives us 2 to the 5th, and that's equal to 32. Okay, so our T of n is going to be 2 raise it to the n minus 2 power. Okay, so when you start with a fraction like that, and you're going to see how it progresses, how it's going to be able to go from one number to the next, and so on, then you have to look at what would be the function that you would apply to be able to calculate, right, a later value in that sequence. All right. Example 6, we have 1, 3, 6, 10, 15, 21. And when we start with the first value, which is 1, when n is 1, we have to achieve 1 here. So if we square 1 and we plus 1 and we divide it by 2, because if you have 1 squared, that's 1, plus a 1, that's 2, divided by 2, that's going to come back to 1. Okay. And then we would then go to the second element, n is 2. Then we would take n and we square it. So 2 squared plus 2 divided by 2, which gives us 3. 6 divided by 2 is going to give you 3. When n is 3 here, we would have 3 to the second power plus 3 divided by 2, which gives you 12 over 2 or 6. So we can conclude that when n is 7, we would take 7, raise it to the second power, plus 7 divided by 2, which gives us 28. So our t of n is going to be n squared plus n divided by 2. Okay. So naturally, we would see how recursion would apply in this situation, right? Because we can go from one number to the next. So the next number is going to build on the prior number, or in this case, if we don't use recursion, we have to create a domain function that's going to represent our sequence. Any question? Okay. What about if they're all the same number, right? Like 1, 1, 1, 1, 1, 1. And sometimes you have that. So if n is 1, it's 1 over 1 is 1. If n is 2, you take 2 divided by 2, you get a 1. If n is 3, you take 3 divided by 3, you get a 1. So if n is 7, then you would take n divided by n, right? Or 7 divided by 7, you still get a 1. So your t of n is going to be n divided by n, or 1. Or it can be also written as t of n is n to the 0 power. Okay. So we have to really write the function by using the position of that element, which is n. And in recursion, we would write the function that would represent the prior element relationship to the value. Okay, so that's why it's n minus 1 is used. Question? All right, so let's tackle the first one. It's a tricky one. So you heard me, I said earlier, sometime certain sequence is funky, right? It starts later and you would have some static value that's just not part of the sequence. Okay. So here you have a sequence called S in the assignment for the first question. And it gives you 1/2, 1/6, 1/8, 1/10, and so on. So you can start with, if n is 1, right, your t of n or f of n is going to be 1 over 1. If n is 2, we would take f of n is going to be 1 over 2. But wait a minute, that doesn't work with 1/6 or 1/8 or 1/10, right? So we start seeing some pattern for the first two number, and then the third value and on is different. So we cannot apply what we apply in the first two number. So when n is 3, we would say that f of n or t of n is going to be 1/2 times n, or 1/6. And then when, I'm sorry, 1 over 2 times n, I should clarify, that's going to be 1/6. When n is 4, your t of n is going to be 1 over 2 times n, or 2 times 4, that's going to be 1/8. And then when n is 5, we can expand it to the fifth element, then that will be 1 over 2 times 5. That will be 1/10. So in this sequence, the first two terms are, that's going to be represented by, let's just say represented by, f of n is going to be equal to 1 over n. And the next part of the sequence, the pattern change. So the sequence pattern starts on the third term and forward. Okay. So the first two terms, there is a pattern, and then the rest of them, it's a different pattern. That's what I'm trying to say. So after the third term, we can conclude that f of n or t of n is going to be 1 over 2 times n. So this is how you write it, okay? The formal way, but you don't have to put it this way. You can just put it in 2 lines, and that's okay. So we would use the large bracket, and we would say that n, when n is 1 and n is 2, the sequence for those two is going to be 1 over n. And I'm simply using insert formula for this, or equation in Microsoft Word. And then I added the symbol and or the bracket, and then I type it in. But you don't have to do it this way. It's just, I want to show you the proper way. So when n is greater and equal to 3, your f of n is 1 over 2 times n. So when you look at Fibonacci, or, you know, even Lucas numbers, and we'll play with Fibonacci down the line. For those of you who took my CIS7, we did Fibonacci in assembly. Okay. You would see that Fibonacci is similar to this, where we would have the 0, 1, 1, and then it's going to take the 2 number, it's going to add it. So it has a seed value that's different, and then the rest of them are going to be the sum of the 2 prior. Okay, so you might run into sequence that would be like this. Okay, so if we need to determine the 6th term of our sequence, we simply applied our equation. F of n is going to be equal to 1 over 2 times n, or for the 6th term, we would say 1 over 2 times 6, which is 1 over 12. Okay. Any question? All right. So I want you to write the function that represents number 2. Okay, so we would start like what we've done in the example. And then we have to answer what is the next term in S. So we can say that there is a common ratio, and it's important that we identify that, as in some of the others. we would start with if n is 1, our f of n is going to be 5 times 1, which gives us 5. If n is 2, f of n is going to be 5 times 2, which gives us 10. If n is 3, f of n is 5 times 3, gives us 15. Okay, so we can conclude that our t of n or f of n is going to be 5 times n. So our fifth value is going to be 25 because we simply take 5 times 5 for the fifth value. That will be 25. So if we need to determine the 22nd value, right, we would take 22 times 5. That's going to give us the 22nd value. Any question? And some of you will be quickly doing this in your head, right? Mathematical approach is to write things out so that way you can trace back and look at your error if there's an error. And for those of you who are taking pre-cal and cal, right, you have to write your proof. So every step you want to be clear. So in the case where you need to work backwards, to be able to find the area that you need to improve on. All right, any question? We're gonna do quite a few of these. So number 3, we have S is 5, 7, 4, 14, 3, 21, 3 over 21, and 2 over 28, and so on. What is the next term in S? And write the T of n equation that represents the sequence. So we would start with if or if n is 1, your T of n is going to be 6 minus 1 divided by 7 times 1. There's always going to be a relationship that you want to draw with the value and the position of that value. Okay. When n is 2, we would have T of n is 6 minus 2 divided by 7 times 2, which gives us 4 over 14. If n is 3, we would have T of n is 6 minus 3 divided by 7 times 3, or 3 over 21. So we can conclude that T of n is 6 minus n divided by 7n. Don't worry, next week, and also later on today, you are going to be able to have a better way, faster way to write your equation when we talk about progression. So manually, when we do this, right, we have to write down our term and how it relates to the position of that term. So for the fifth term in number 3, that will be 6 minus 5 divided by 7 times 5, which gives us 1 over 35. Very easy. Any question? So this is a little more complex than the few that we've done, right? In that you see that there's a presence of n in the numerator and the denominator. Okay, so I'm going to stop there. I'm going to switch back to the notes because we got to talk about progression now. Okay, so quite a few examples at the beginning of our notes. And then remember the one that we just did, right? There's another one that's similar to that there on how you would write the first one that's going to be different and so on. So in the next part on page 3, let's start defining arithmetic sequence. So an arithmetic sequence is a sequence that each term equals to the preceding term plus a constant. That means that you would add a constant to the prior term to get to the next. And for the arithmetic sequence, the difference between the consecutive term is always the constant, or it's always the same. So we would say that we can have a difference or a distance. Some textbook or some tutorial would say distance instead of a difference. So when you look at the sequence, you start with A, and then you would add D to A to get to the next number. And D is going to be that constant or that distance between the two. And then for the next one, that will be A plus 2D, right? Because you do A plus D here. That gives you A plus 2D. And then again, A plus 3D. And A plus 4D and A plus 5D and so on. So in that, we can conclude that for any arithmetic sequence, the T of n, the equation would be A plus n minus 1 times D, which is our distance. Okay, and A is going to be your first value. And D is going to be the difference, that constant between the terms. Okay, so let's look at 1111. You're given a sequence 4, 7, 10, 13, 16, 19. Without looking at this, you would know what is A. A is going to be the first value, 4. What is D? You would take the next number, subtract the previous, because it's always going to be the same as you check throughout your sequence. So if I take 7, subtract 4, I would get a 3. So here we can say that the first value is 4, which is A, and the distance between the values, it's going to be 3. So it asks you, what is the next term? And we're going to use this equation, right? So here we would see that it's asking for the 7th term. So we would then plug A into this equation, which is 4, plus, right, n minus 1. So if I'm looking for the 7th position, I would plug in 7 here, subtract 1, which gives me 6, right? 6 times 3, that's 18, plus 4, that's going to be 22. So the equation that represent that sequence, this sequence right here, once you plug in the A and you plug in the D, you should be able to come up with the T of n, 3n plus 1. So all you need to be able to write out that equation is the first value and the distance in between. That's if it is an arithmetic progression, meaning that the difference between each for two terms, right, and all the subsequent term is going to be a constant, same number. And in this case, it's 3. Now, if it is not, then it is not an arithmetic sequence. So let's say that if I have 3 here and then 4, and then 5, and so on. So it is a progression in itself, then that's not an arithmetic sequence. Okay, question. All right, let's do one more before we tackle the next exercise. So example 11, 12. We have -7, -1, 5, 11, 17, and 23 in this sequence or partial sequence. Okay. So we can identify that our A is going to be -7. And what is our D? You take -1, subtract -7, which gives you 6, or you can take 5, subtract -1, same. That's going to give you 6. So our D is 6. Then we would use this equation. T of n is going to be A plus n minus 1 times D. So you plug in the A and you plug in the D and you distribute, right, with 6 times n minus 6 times 1 there, which gives you 6n minus 13. And that's your function that represents the sequence. Now, once we have that function, we simply plug in the 7th term. So -7 plus 6 times 7 minus 1, which gives us 29. So the next term after, right, 23, it's going to be 29 because it's going to add 6 to 23, which gives us 29. Sure, you can do addition, right? But let's say if they ask you for, you know, 5, the 54th position, what would that be? It's better that you have the equation. So make sure that we know this. We know how to do arithmetic progression for our test, quiz, and final exam. And so as you can see, there's another example. So let's do the assignment now. Let's look at progression in our assignment. Oh, I forgot to do number 4. But 4, we can use progression. All right, number 4. We have 13, 16, and 19, right? The old way is to write all of the steps out, right? When n is 1, when n is 2, and when n is 3. But now we have an equation to work with. So you first identify your A. What is your A? A is 13. Then you take 16, subtract 13, which you're going to get your D or your difference. Or you can do 19, subtract 16, doesn't matter. So we have our D is going to be 3. So for our 4th term, T of 4, we would take 13, which is our A, plus n minus 1. So 4 minus 1 times 3. And when you calculate this, you get 22. So how did I get from here to here, right? Instead of writing this out, just like what I've done, you've seen in the example, you can say f of n is going to be equal to, and plug in your A, which is 13, plus your n, keep it the same, minus 1 times your D is going to be 3. Okay, so you can put times 3 like this or type 3. Then you would have, you know, if you distribute everything out, that will be 13 plus n, or sorry, 3n minus 3. And then we just want to do the subtraction, so we can reduce that. So that will be 10 plus 3n, which is our function. So plug it into that equation using the a and d that we found and keep the n. And so here's your equation. That's how I got that. Any question? Okay, let's talk about number 5. And you might see something like this on the quiz where it gives you different equations and you have to pick the one that represents arithmetic progression. Okay, so for A, it asks you, the question asks you to determine which one is an arithmetic progression. You would have more than one answer, but for the quiz, you're only going to have one. Okay, so in this one, we have 2 answers. So the first option is A, and A says T of n is going to be 8 times n. So if you write out the sequence, you can see right away on how it progressed. We have the first value is 8, second, right? 8 times 1 is 8, second is 8 times 2 is 16, and so on. So you can see that the difference between the two is what? 8, right? So I take this plus an 8. So that definitely that's an arithmetic progression as you add the constant, which is 8. What about T of n is n plus 1 divided by 4n? No, it's not, right? If you wanted to test it, plug in 1, plug in 2, plug in 3, and you can see. If it's not adding the constant between from 1 to go from 1 to the next value, then it is not an arithmetic sequence. Okay, when you see an exponent in the mix, definitely not like this. Okay, so C is out. For D, we would say, okay, let's test it, right? So I did T of 1, I have -9 plus 6 times 1 minus 2, I have -15. T of 2, -9 plus 6 times 0, which is -9. T of 3, the result for that is going to be -3. So we have a progression, right? Which is 6, because you add the constant 6 to get to 9, 9 add 6 to get to 3. And so there you go. So for D, right, D and A are your answer for number 5. So you can just highlight those options. So now let's go the other way. What if we're giving an arithmetic equation and we need to put that into a partial sequence? Easy. Take the equation and plug in the n value, which is your position of your term or your element. So we would start with T of 1. That will be 5 right here times 1 minus 2, which is 3. T of 2, take 5 times 2 minus 2, which is 8. T of 3 takes 5 times 3 minus 2, which is 13. T of 4, 5 times 4 minus 2, which is 18. There we have it. That's good. So we can say our sequence is 3, 8, 13, 18, and etc. Any question? So tying this back to what we talked about last week about implementing algorithm for search and sort, but algorithm in general. So once you have your equation already, right, you can now incorporate that into your program. Okay. If you want to refer to the equation that we learned from for the arithmetic, you can definitely do that. Okay. To just represent what n is, right? And that's what you're going to see this week, right? Then you have to define what D is and what A is, and then, include algorithm STL, and then write out your equation, put that into a loop and have it loop so it builds out your sequence and print it with a for loop, right? Easy. Okay. So when you look at this, you said, oh, if I can solve this in math, I would be able to plug that into a programming language and write it. Okay, so all we simply do here is to iterate through what n could be based on the element value, right? And then applying our function here. Okay, let's do the next one. Also in another arithmetic sequence. So here we're given -4 plus 8 times n minus 1 for number 7. And we need to come up with the partial sequence. So you plug 1 in for n to start. So -4 plus 8 times 1 minus 1, which gives you -4. Then we plug in for n is 2, t of 2, -4 plus 8 times 2 minus 1, which is 4. And then t of 3, we would calculate that out and get 12. And then t of 4, again, we would get 20. So now we can write out our sequence, which is -4, 4, -12, and 20. Right? So put that into a sequence format for number 7. Any question? Okay, no question. All right. So the next part is going to be on geometric sequence, right? What if we don't add a constant? What if we multiply to go from 1 to the next number? Okay. So we would talk about geometric progression. Go to your notes. So geometric sequence or progression, it is a container that holds terms, and the terms is one term is different than the next term through a ratio. So we would go from one term to the next by multiplying the previous term with a constant. Okay. And it says that the sequence of numbers where each term after the first is found by multiplying the previous one with a fixed non-zero number called a common ratio. And repeatedly, it's defining it in 3 different ways, so that way you know. But the equation that we would use is this one. Okay. So your T of n is going to be a times r raised to the power of n minus 1. And it's always the same for geometric sequence. Okay, and a again is the first value, and your r is the constant that you're multiplying the previous number with. That common ratio is your r. So when we look at example 11.14, we would look at 2, 6, 18, 54, 162. What's RA? 2. What's RR? 6 divided by 2, which gives you a common ratio 3. Or you can take 18 divided by 6 just to check. Okay. So it asks us, what is the sixth term? That's easy. Plug it into the equation. So our T of n is going to be 2 times, right? R is your 3. That's your common ratio. Raise it to n minus 1, which is 6 minus 1. That's going to be 5 for the exponent. So that's equal to 486. And then similarly, using the same technique, we can solve for the next example. So, and the important takeaway from this is when you apply this type of equation, you need to first identify what A is and what is your R, your common ratio, by taking one number divided by the previous. Okay. All right, let's solve our assignment question. For number 8. Select the options that represent the geometric sequence. Okay. And I try to trick you here, right? So if you want to do this, you know, the simplest way is to plug in the n value, like what we've done in the prior question. When n is 1, is this. When n is 2, when n is 3. And you would see if there's a common ratio. If there is, you're good. Okay. So the question A is really easy. It looks almost like the equation, right? You can plug in for A as 10 and then 3 for R. So that's a given there. So A. Okay. What about B? Okay. If you're looking at the sequence, what's the difference between one number to the next? Is there a common ratio, you would ask? So 2 divided by 1 is 2. 4 divided by 2 is 2. Yes, that is a geometric sequence. As it would get to the next number by multiplying the previous number with the common ratio. So B. What about C? Okay, be careful with this one because there's a plus. It's not a multiply, right? So no, it looks almost like it, except for that it adds instead of multiply. So not C. What about D? Right, if you want to be careful, you want to check it, you can plug in, but no, this is not. So whenever you see the added term here, it's usually not. It should be close to this format, or when you calculate it out, there should be a common ratio in your sequence. So A and B is your answer for 8. And you're going to see quite a few questions like this on quiz and tests, right? As we are using Canvas with multiple choice, so we have to find different ways to assess you. All right, let's do number 9. It provides you with T of n is 64 times 1 over 2 and raise that to the n minus 1 power. It asks to provide the initial part of the geometric sequence. That's easy. So we would start with when n is 1, T of 1 is 64 times 1 over 2, raise it to 1 minus 1. And this is going to be exponent 0, which makes this number 1, right here. So the result is 64. When n is 2, we would then take 64 times 1 over 2, raise that to 2 minus 1 exponent. And that gives us 32. And you're going to start seeing the pattern. When n is 3, 64 times 1 over 2, raise it to 3 minus 1 power, which gives us 16. So you see the common ratio now, right? Okay. So there you go. So now you would have your sequence. So your common ratio, your R, is this number, half. Any question? All right, number 10. So same as the last one, we are given the equation T of n is 3 over 7 times 2 to the power of n. So we would start with n is 1, plug that into the equation. So we have 3 over 7 times 2 to the first, which is 3 over 7 times 2, or 6 over 7. And it's fine, you know, in this class, I'm not going to ask you to reduce your fraction. Okay, you can leave it like that so you can see the pattern. In other classes, they might ask you to reduce it to the simplest fraction. That's fine. But for this class, I prefer that you leave it like that so you can see the pattern. For T of 2, we would plug in the equation again using 2 as n, and you would have the result of 12 over 7. T of 3, again, we would plug 3 in for n, and we would have 24 over 7. And you start to see that 6, 12, 24. What's next? Okay. So, and the bottom, the denominator is the same, right? 7 each time. So here, right, when we look at the common ratio, we can simply take the next number divided by the previous, which gives us R is 2. Any question? All right, no question on geometric progression. So you're expected to know how to use the equation, or which equation is used for which progression or sequence. Okay. And then to be able to apply the equation using the n value. Some questions will ask you to select the option that would show the sequence. Some would ask you to select the equation, and so on, or a certain value at a certain element position. So you have to calculate it out, like what we've done with, you know, the 7th value or the 5th value. It's like that. All right. Next part is going to be on quadratic. So quadratic sequence is a sequence in that the nth term is given by the quadratic equation. And we would use a of n is going to be 2 times n squared plus b times n plus c. And if you explore quadratic equations before, this is the format for quadratic equations, right? So in this example, 11, 16, it's given you 1, 4, 9, 16, 25, 36. How did we get A of n is equal to n squared? Well, use this equation, okay, and be able to plug in, okay, and we will discuss this. So to really expand, let's come back to this. Let's really expand on this. This is what you need to know. In quadratic equation, it is the difference between the successive terms that's given by the linear function and the second difference in the constant. So what you've learned in arithmetic sequence is a linear function, and the difference in the successive term is a constant. Now, the difference between quadratic and arithmetic in that it takes a second difference. So it is a difference of a difference. So when you're looking at the pattern in the sequence, right, in arithmetic, we would see the distance between one number to the next. For quadratic, there is a pattern in the difference from one number to the next. It's not a constant. So we would see, let's say from one number to the next, that will be 3, as in the difference, and then 4, 5, 6. So the D is increasing or decreasing. Okay, so there's a second level of difference in that it is not a constant that's applied to determine the next value, but is a progression that is applied to determine the next value. Okay. All right, so what do I mean? Okay, so let's take the sequence, for example, 6, 15, 28, 45, 66, 91. First, let's find the difference between these values. So if I take 15 subtract 6, I get a 9. 28 subtract 15, I get a 13. 45 subtract 28, I get a 17. 66 subtract 45, I get a 21. 91 subtract 66, I get a 25. So the difference at the first level is a progression, you see? Okay, so I have 9, 13, 17, 21, 25. Those are the difference between the two numbers. Then I take a difference off of those, right? Take 13, subtract 9, I get a 4. 17, subtract 13, I get a 4. So at the first level, right, the difference is an arithmetic progression. I'm sorry, a progression. And then the second level, it is an arithmetic progression. Okay. So we would need to find the second differences for quadratic. Now, in order to do that, what we would do is we would plug in A, okay? We would plug in N, and we need to solve for B and C. Okay, so let's take a look at this. For the step 1, right? I plug in N is going to be equal to 1. So I would take A times 1 squared plus B times 1 plus C. And I keep A, B, C the same, okay? No change. So I only plug in the N. So when you reduce that, you would have A plus B plus C is equal to 6. So simply plugging in N is 1. When N is 2, again, we would plug in for N. And we can write that out, and we can reduce it down to 4a plus 2b plus c is equal to 15. And then n is 3. Again, right? We write that out, multiply it by a, b, and c for n. And that's, we have 9a plus 3b plus c is 28. So then, because we need to find the differences, we would then take the first two equations from the result and we subtract. So I would take 4a plus 2b plus c equal to 15, which is this one. Subtract the first one when n is equal to 1. So I take when n is equal to 2, subtract n is equal to 1. Because remember, when we did the arithmetic progression, we take the next value, subtract the previous. That's what we're doing. We're taking when n is 2, subtract when n is equal to 1. Okay? So you line them up. 15 subtract 6, I get a 9. C subtract C, I get a 0. 2b subtract b, I get a b. 4a subtract a, I get a 3a. So the difference between those two is 3a plus b. I'm not done. Then I would take the difference between, right, when n is equal to 3 and n is equal to 2. Okay, for the next two numbers. So I take 9a plus 3b plus c equal to 28. Subtract 4a plus 2b plus c equal to 15. Line them up and subtract. 28 minus 15 gives me 13. C subtract c, I get a 0. 3b subtract 2b, I get a b. 9a subtract 4a, I get a 5a. And I know that this concept is covered in college algebra or algebra in general. So, right? And also sometime pre-cal, they covered this to review. All right, so once we have the difference between the third equation and the second equation, which is n is 3 and n is 2, then we're going to take the result from that, subtract the other result to get a and b. Okay, so I have 5a plus b equal 13. Subtract the first one, okay, 3a plus b equal to 9. Line them up again and do the subtraction. So here we would have 13 minus 9. I have a 4. A b minus a b is a 0. 5a minus 3a, I get a 2a. So once you're down to a single variable, it's easy, right? You can solve for it and then plug it back in to solve for the second variable and then the third. So I divide both sides by 2 to get my a, and a is equal to 4 divided by 2, which is 2. So now I have my 2. Then I plug 2 in for 3a plus b equal to 9. So if I plug a in is 2, that gives me 6 plus b equal to 9. Now I'm again down to a single variable, so I can solve for b. Subtract both sides by 6. Then I have b is equal to 3. Now I have a and b. I need to solve for c, right? So then I would take 2 for a plus b is 3 plus c is equal to 6, which is our first result for the difference, right? Then my c, so this is equal to 5, subtract both sides by 5, I get c is equal to 1. So once I have a, b, c, I plug it back into the original equation for quadratic progression, I would have 2 times n squared plus 3n plus 1. Okay, let's solve for the next one. Okay. So for number 11, it asks you to select the options that represent quadratic sequence. It's very obvious, right? The options that I gave you. So A should jump out at you screaming quadratic equation because it is in quadratic equation format. When you see the first, right, it's going to be n squared like this, right? Plus, here's a 6n, okay, and then the 1. So that's like a times n squared plus b times n plus c. It's exactly that format. So A is an option. And also D. D is the same, except for that this is a subtract. So think of it like adding a negative value there. So A and D is the answer for 11. So the difference between arithmetic and quadratic in that arithmetic sequence is given by a linear function, and the difference between the successive term is a constant. This is in the notes. In quadratic sequence, the differences between successive terms are given by linear function, and the second differences are constant. So not until the second level in quadratic that would be a constant. Any question? We still have to cover series today, so not too bad. We're like halfway mark. Okay, any question on 11 and 12 or 12? All right. Okay. So let's solve for this. So 13 is long, and bear with me, right? I tried to illustrate it like how the notes does it and all the crazy highlights. Okay, so we're given a sequence for 8, 11, 13, and 14. So what I did was I put it into a table, and I would find the first and the second level of difference. So that shows you, right? But you don't have to do that. Okay. So the first level of difference, we have 4, and then 3, 2, and 1. So it is a sequence in itself there. And then the second level of difference is going to be a 1. Okay. So this is the equation that we're going to use. And you simply start with plugging in n is equal to 1 to that equation. So when we plug that in, we would have a times 1 squared plus b times 1 plus c. So that will be a plus b plus c is equal to 4. That's the first value, 4. Then for n is equal to 2, we would then again plug that in, and we would multiply everything out. So that will give us 4a plus 2b plus c is equal to 8. And then Lastly, for n is equal to 3, we plug 3 in for n. So we would then find that 9a plus 3b plus c is equal to 11. Okay, so once we have the equation, right, that as a, b, and c for n is 1, 2, and 3, we would then find the first level of difference. So you would take the equation where n is equal to 2, you would subtract it with the equation where n is equal to 1. Line them up. So 8 subtract 4, we get a 4. C subtract C, we get a 0. 2b subtract b, I have a b. And 4a subtract a, I have a 3a. And then after that, we would repeat the process by using the third equation where n is equal to 3, subtract the second equation where n is equal to 2. Okay, and that is here. So I would have 11 subtract 8, I have a 3. C subtract C, I get a 0. 3b subtract 2b, I have a b. And 9a subtract 4a, I have a 5a. So now we achieved the first level of difference. Then once we have the result from the first level of difference, we would then take or find the second level of difference by taking the output from the first level and subtract them. Okay, operate subtraction there. So I would take 5a plus b equal to 3, subtract 3a plus b equal to 4. And so I would have 3 minus 4, that will be negative 1. A b, subtract b, it's a 0. And then 5a, subtract 3a, I get a 2a. So divide 2 on both sides, that gives me a is equal to negative half. Once I have a, then I need to find b. So I use this equation, 3a plus b is equal to 4, and I plug a in and solve for b. So after we operate the arithmetic for this, we would have b is equal to 11/2. Now I have a and b, then I can solve for c. So then I would plug a and b in. Okay, give me 1 second. Let me move this up a little bit, or let me see if it's going to hit it. Yep. Okay. So then I would have a and b plug into my equation a plus b plus c is equal to 4. Recall that from the top. And so I can solve for c. So a is negative half, b is 11/2, and then plus c equal to 4. Okay, so negative half plus 11/2, that gives me 10/2, which is 5. And then subtract 5 from both sides, so c should be negative 1. So after I have a, b, and c, I'm going to move this down a little again because it's cutting off the second part. then I would be able to put it into the quadratic progression equation. So I have a here, negative half times n squared plus b, which is 11 half times n minus 1, which is c. There are other techniques on how to solve this, but this is very transparent in that we would see the progression at 2 levels for quadratic. Okay. Any question? So I still have about close to 30 some minutes. So we'll cover series next, which is sum. So we do have a quiz in the next week or so, right? To cover the last couple of chapter, like 8 and then 9 and this one. Okay, so that's gonna hit the chapters that we went over. Okay, so before we solve this, let's look at series and Gauss trick. So series is the sum of your sequence. Okay, sequence just, you would see that there's progression or a pattern in the number for your container. Series when we add everything up, and you can have a partial sum or you can have a complete sum. In the case where if we have infinite sequence, sometime we would just determine the partial sum, right? For let's say the first 100 numbers or the first 10 numbers and so on. So when you refer to the sum of the sequence, that will be defined as series. Now, it says that the sum of the first n term is called the nth partial sum. So now we're going to talk about Gauss trick. And Carl Gauss was a brilliant kid. He was given a task by his teacher, either as punishment or something like that, just to keep him busy. And he was told to add for all the numbers from 1 to 100 or 1,000. I think it was 100. Yeah, no, it says. But he found a shortcut to it using just arithmetic operation. If you take the number of the terms and you divide it by 2, multiply it by the first and the last term sum, you get the partial sum or the sum for the series. Okay, so this is Gauss formula right here. So Gauss formula says that we would take the number of terms divided by 2, multiply it by the first plus the last term. Okay. All right, let's check out our example. So when we look at 1 to 100, right? So we would take the total number of terms, which is 100, divided by 2. Okay. Times it by the first and the last term added, which gives you 50/50. And then the same thing for the next one. But in the case where you have ns to represent that last value, you would take n divided by 2 times n plus 1 for this one. Okay. So God's trick makes it really easy in the case where we have a very large sequence to add together to find the result for our series, right? So then let's tackle the next one. So determine the arithmetic sum for the following sequence. I have -72, -60, -48, 36, -24, and -12. So based on Gauss trick, you would take the number of terms, and we're talking about the partial sequence now, right? The partial sum. So we're not talking about the whole thing because it can go infinitely. So here I count up the terms. I have 2, 4, 6. So I would take 6 divided by 2, multiply it by the first term, which is -72, plus my last term, which is -12. And I would have the result as -252. Yes, you can sit there and add everything, each one by one. Okay. But the equation allow us to work with a larger partial series. Okay. A larger in that when we have, let's say, further down the line, we will be able to find the sum for that sequence. Question? So make sure we know how to do series, arithmetic, geometric for our tests and quiz. All right. So I only have one exercise for that, but we will also revisit this as we continue in the next couple of weeks. So this class is designed to build on the concept that you also covered prior. So sometime we would revisit it. You would see the correlations in these theories in the things that we're learning for discrete. So the geometric sum is the sum of your geometric sequence. Remember that these use common ratio, right? And yes, you can sit there and you can add them all together. Okay, so here it shows you how they're able to derive the sum. But there has to be an easier way, okay, by using the equation. And I put the notes for the book. So this is the equation that you're going to use, this one. The bottom of 8. So we would have a times 1 minus r to the n divided by 1 minus r, in that a is the first term, r is the common ratio, and n is the number of terms. Okay. So when we look at this example, I thought I included that. Actually not. Let's do the assignment so we have some practice. Let's look at number 15. Okay. And we are going to finish early. How about that? I thought that I would make it to the end. Okay. So geometric sum for the first 4 term, and sure, you can punch this into your calculator and find that out real quick, but that defeats the point of using the formula or learning how to do that today. Okay. So the first 4 term, and we know that R is going to be 3. How did I come up with a common ratio? I take 30 divided by 10 or 90 divided by 30. I have R is 3. Then my N is going to be the number of terms, and it asks us to do 4 terms. So, or we can do 6. That would just be a larger value, right? So the first 4 terms, and your A is going to be 10, which is the first value. So when you use that, let me copy this real quick, 1 second. Okay, so I can show you. Copy this. Okay. So when you use this equation, you simply take A, which is 10, multiply it by 1 minus 3, 1 minus R, right? 3 is your R, and raise it to the N value. So that's 4, because we're doing it for 4 terms. Then divide it by 1 minus 3, which is 1 minus R on the bottom. And make sure that we apply the parentheses appropriately. Otherwise, your calculator is gonna not treat a certain thing as together and separate it, and it's gonna mix up and give you the wrong result. So you should have 400 as the output. Okay. So make sure we know how to calculate geometric sum or geometric series. And we're going to see how the computer does it when we program it in C++ this week. That's it for the assignment. Any question? So just to sum it up, right? We covered your arithmetic progression today by starting out with looking at just, what would the value be when we plug in n, and then we transition to arithmetic progression or sequence. Then we cover geometric sequence, we cover quadratic sequence, and then we cover the geometric sum and arithmetic sum, or arithmetic series and geometric series. Okay, so that's the true difference, is when you say series, it's a sum of your sequence. Okay, and then sequence is, it's not a series. Okay, so that's all I have for you for today. I'm going to stop